Optical Time-Domain Reflectometer, also known as OTDR, and Fiber Optic Cable Testing Overview. OTDR reduces the mean time to repair by detecting problem areas. Interpretation of OTDR traces requires knowledge of the specifications of the fiber infrastructure under test, use of accurate test parameters including distance, time, pulse width, which is resolution, knowledge of connector types used and average values of insertion loss and reflectance for each connector also aids in the interpretation of OTDR traces. Fiber is essentially a glass conductor carrying optical signals or light. The most important specifications of fiber are index of refraction. The index of refraction for a vacuum equals the speed of light. The index of refraction is lower for other mediums. Two important parameters measured by OTDR are insertion loss and reflectance. The higher the reflectance value with a positive number, the less light is reflected back. Typical reflectance for UPC connectors is about -50 decibels to -55 decibels. Typical reflectance for APC connectors is about -60 decibels to -65 decibels. In today's 10 gig networks, -45 decibels or better reflectance is sought. OTDR settings involve three important parameters: distance, the length of the fiber under test; time, the duration of the test, typically between 15 and 30 seconds, but no more than 45 seconds, and pulse width, which determines the resolution. A wider pulse width provides more power for covering longer distances but less resolution. On the other hand, a narrower pulse width offers more resolution but less power. For instance, a 5 nanosecond pulse width corresponds to about a 1.6 feet wide pulse, while a 100 nanosecond pulse width equals about a 33 feet wide pulse. Longer pulse widths create dead zones that are not detectable. If two reflective events are within close proximity, they may not be visible clearly due to the dead zone. Reducing the pulse width allows both events to be seen clearly. When using OTDR, the best practice is to start with auto trace, which uses the standard settings of distance, time, and pulse width. Determine the dead zone using reflective events that are within close proximity. Adjust the pulse width or resolution until the dead zone is eliminated. When the dead zone is eliminated, both reflective events can be seen clearly. Multiple wavelengths used for single-mode fiber testing are 1,310 nanometers and 1,550 nanometers. For testing at multiple wavelengths, the best practice is to test at 1,550 nanometers first. If the test fails at 1,550 nanometers, then test at 1,310 nanometers. If the test does not fail at 1,310 nanometers, it is likely a pinch or microbend issue. If a pinch or microbend is suspected, perform real-time tracing and have someone check the fiber in the field while testing in real-time mode. Some pinches or microbends that may exist in cable trays act as attenuators, and their elimination may result in high optical power in some applications.